Could you weld it, but with like an extra piece over it as well,
Yeah,
to kind of merge
good.
it together?
That's about right, and I can see Lewis has got similar ideas. So the suggestions are some kind of replacement, some kind of extra piece, or some kind of weld. And I think those are exactly the ideas to be thinking of. About a week after this happened, or a week after this was found, this is the solution that was proposed by a Scottish engineering company, which I think is quite a nice one. It's in between that replacement and the extra piece, but it's kind of putting a jacket around the whole thing, which you hope will be stronger than the original girder was, and then that gives you the structural integrity back, and you can work with that until you can have some kind of long-term solution. And I guess the long-term solution might well involve re-welding it as well, although we'd need to check whether welds are stronger or weaker in the long run than the original material. My guess is they might actually still be weaker than the original material. That's exactly the kind of engineering design, both what people have just suggested and what we're looking at on the screen, that, you know, if you're able to do those things and make them work, the world will beat a path to your door, and you know, you'll be hugely employable and doing interesting things. So it's a very practical bit of work. Okay, so before I start talking about stress and strain, I'm actually going to talk about something which is similar but much more limited. And you may have seen this before if you've done either physics or engineering before you started as an EPD student. You will have seen similar things, I think. This is Hooke's law, and it's very specifically about springs, by which I mean what I hope everyone pictures when they think of a spring. The most typical example is like a coil of metal where when you push it down, it pushes back up again. And in fact, you can say something with springs about the kind of force with which they're going to push back. The force is this constant K multiplied by delta X, and delta X is a change in length. So what that tells us, K is just one number. So the more you change the length, the higher the force you get in the spring. And that's kind of an important first thing just to remember. Yeah, Omar, question. Was it a question? You're still on mute. I saw a hand go up and then come down.
No, sorry, that was an accident.
Okay, cool, no problem. But do anyone who wants to put their hand up, I'll keep an eye on it, and happy to discuss as we go through. So that's what we've got. F is a force in this equation. Delta X is a change in length. I think I've already mentioned this Greek letter delta. That's a capital delta, sort of a Greek letter D. We use that for change. So delta X is a change in X, the length of something. And then K is what's called the stiffness, and that's a property of the spring. So this is what I've already said, that the change in length is proportional to the force, and you can work out what the units of the stiffness must be. Remember, we've said in the past, in previous lectures, that the units on the left-hand side of an equation must be the same as the units on the right-hand side of the equation. So if F is a force and delta X is a length, K has to have units of force divided by length. That's newtons per meter, newtons divided by meters. There's just one last thing to say. Anyone who has sort of handled a fairly soft spring will know eventually you can pull them so far that they behave completely differently and they don't spring back anymore. And that point is called the elastic limit. And after that, the deformation is called plastic deformation. And everything that's on this slide is only true up to the elastic limit. So you can apply a certain amount of force to a spring and it'll follow this law. And then if you go past that certain amount of force, it'll stop following this law. So what does that actually mean? This is a slightly clunky slide visually, I acknowledge, but the idea is for every extra weight that you hang off a spring, you'll get the same amount of extension again. So when we move to W, 2W and 3W hanging off the spring, we move to delta X, 2 times delta X and 3 times delta X extension. And that gives you a nice straight line on a graph. And in fact, the slope of that straight line is the can tell you the stiffness of the spring. So that's one way we can get the stiffness of the spring. So here is an example. If you look at many vehicles, they'll have springs somewhere in their suspension. This is a coil spring here with a kind of helical shape, just like we've sort of been talking about. And as you sit on the snow scooter here or on a motorbike, or as you get into a car, those springs will compress a bit because your weight adds to the force on the spring. And we know now that the force is proportional to the change in length. So when you add some force, you're going to get a change in length. So here is an example. And what I'm going to do is give everyone 3 minutes just to write out or to have a go at answering this question. We'll make it 4 minutes, I think. And I'll just make sure I've got my camera set up so that we can look at how to answer it in 4 minutes' time. That is about 4 minutes. So let's have a go and see. Did anyone get to an answer?
Yeah, I think so.
What'd you get, Harry?
So for the first part, I got 10 newton meters to the power of -1. I don't know how you say it properly. And for the second part, I got 125 millimeters displacement.
Cool. So the displacement of 125 millimeters. And I mean, one of the things that I'll keep encouraging everyone to do is to kind of have a gut feeling here as well. And that fits with a gut feeling for me. 20 kilograms causes a change of 50 millimeters. So reasonably enough that when you get to 50 kilograms, you expect it to be a bit more than double 50 millimeters change. So 125 sounds pretty good. Let's just work through the maths of that so everyone can make sure that we're happy. I'm going to see if I can do a split screen on this with that one and that page. I guess we'll just leave it like that. And I hope everyone can see on the right-hand side my working. Sorry, the camera, there's a light directly above, so the camera's casting a shadow on the page, but I guess we'll be able to work with that. So what I've done is just to try and draw out a fairly simple diagram of no load. The spring is 750 millimeters long. When we've got 20 kilograms, the spring is 700 millimeters long. And when we've got 50 kilograms, we don't know what the length is, and that's the question. Just because I always do these things, I've converted millimeters into meters. And also what I've done is take the masses and use weight is mass times gravity to give me a weight, which is a force. So converting millimeters into meters, you don't have to do that. You could just work through the whole question in millimeters, but I always like to convert everything into the SI unit where possible. This bit you do kind of have to do, or you should do, because we're going to use Hooke's law, which is about forces, and it says that force is K times delta X. If I just number these situations as 1, 2, and 3, then the structure that I'm going to use is to use the transition from 1 to 2 to find K, which I don't know yet, and then I can use that to tell me about the transition from 1 to 3. So I'll kind of mark that onto my page. As I go from situation 1 to situation 2, F, the applied force is 200 newtons, and delta X, the change in length, is 0.75 meters minus 0.7 meters, which is 0.05 meters. So now I can take Hooke's law again, F equals K delta X, and rearrange by dividing both sides by delta X. And that will give me K equals F divided by delta X. And in this context, that's 200 divided by 0.05. And I do have a calculator here. I think I've done
it wrong. I didn't rearrange it.
Well, it's interesting because you might find you've done it right, but you'll have a slightly different number. We'll talk about that in a second. Cool. So my number comes out to be 4,000. And then because I know this is a force in newtons and this is a change in length in meters, I'm confident that my units are newtons per meter. If you left everything in millimeters, you'd have a different number for K, and then your units for K would be newtons per millimeter. If we now jump, let's finish this off and then we can look at the whole thing as kind of a big picture. If we now jump to what happens in situation 1 going to situation 3. The change in force now is from 0 to 50 kilograms, so that's 500 newtons. And we know it's the same spring, so we know K is going to be 4,000 newtons per meter. So now we can do the same thing again, just use Hooke's law and say F equals K times delta X. Now we want to know the change in length. That's the kind of final part of the question. So we can say delta X equals F over K, rearranging, which is 500 divided by 4,000, and that will come out to be 0.125 meters, which is the same as the 125 millimeters that Harry got. Again, a slightly pedantic point, but one that can be important in some contexts. What we're actually asked for is the new length. So I'm just going to finish off by writing down the new length is going to be the original length minus the change in length. And so that's going to be 0.625 meters. And I put all of that in, and that's my answer. So I think it's interesting. I mean, we really only had one equation that we were using, F equals K delta X, but we had to first of all use it to find the information about the spring that we didn't know. And then once we had the information about the spring, we had to find how things were going to work out in a new context. And so even when you've only got one equation, you can find quite a lot of new information from it, I think. Any questions about that work that I've just done there? Good. As always, all of this is available on the Moodle site. There are worked solutions up for everything on Moodle, so you should be able to see those. Okay, let's go back to the slides. So that's Hooke's law. It's one equation. I would say it is worth memorizing. You know, we're going to use it enough that it'll be quicker than looking it up every time. And it's one of these things where when you go out and work as an engineer, there might be some expectation that you know it. So it's just worth remembering it now. What we can do next is kind of to go on and take that. You may have been thinking, and certainly when I was at your level, I thought that's fine, but there just aren't that many springs in the world. You know, learning the specific way that springs work isn't going to tell me that much about engineering. But the reason it's in this particular lecture is because if you look at it in the right way, everything looks like a spring. And that's what we're going to go on to now. And instead of understanding using F equals K delta X, Hooke's law, we're going to understand it using these tools of stress and strain. So again, I think this is something everybody intuitively understands, but it's worth just stating it and being clear on it. A compressive force is a force that does some kind of squashing, so it makes an object shorter along the axis that you're applying the force, and a tensile force makes an object longer. So this is a compressive force in the middle, and this is a tensile force on the right-hand side. And, you know, obviously, mostly we don't see things change their shape this dramatically. If this is made of concrete or steel, it would be a tiny amount that it compressed or extended, but nevertheless, it would compress or extend. All materials behave in this way, at least a small amount, and that's why this is becoming, what we're about to get onto is such a powerful set of ideas. So what we're going to work on in this lecture are things called direct forces. That's where we're kind of compressing something in the obvious way along its axis. I'm just trying to find I've got some candles here which won't really compress, but if you can see me down in the corner of your screen, what we're talking about is compressing it along its length. And what I'm not going to do is any kind of like bending it or twisting it or applying a shear force to it across its length. Everything will be along the long axis of the objects we're looking at. Later on, we'll be able to extend that to different, to bending and twisting and all kinds of other things. But for now, the most standard way of looking at something is this kind of direct force. And what we're going to do is define this new concept that I've talked about a lot, and now we have a definition for. Stress is force divided by area. So stress here is the Greek letter sigma. Let me just put that in the chat. And I think that's a lowercase sigma. F is force, which we know about already, and A is area. And what we mean is the cross-sectional area. That means kind of the area the force is applied over. So if I go back to my candle and I imagine I'm squeezing the candle along the length, then it's that area there that we're interested in, the circular area that's kind of supporting that force. Again, that's the kind of thing that I think makes some intuitive sense, that if something is much broader, it will be able to hold up a bigger force. So again, we can do our usual thing of saying the units have to match on both sides. So the units of stress must be the units of force divided by the units of area, and that's newtons per square meter. And we call newtons per square meter pascals. So you might see sometimes this unit being used and sometimes this unit being used, and you have to know that those are interchangeable and equivalent. So let's do an example. I'll give everyone another 3 minutes to have a look at this and a think about it. Okay, that's 3 minutes. Anyone got an answer they want to suggest? "50 kilopascals. That sounds pretty promising to me. I think that's going to be right. Yeah, thanks, Luke. Let's take a look and work through it and check that I get to that number too. So what I've done is just to, sorry, that was a line I drew by mistake. Just to, again, draw out the problem and make a note. 10 centimeters is 0.1 meters, and therefore the area that we're dealing with is that 0.1 squared, which is 0.01 square meters. This is one of those places where I think it is easiest to convert to meters straight away, because otherwise you'll have to convert from newtons per square centimeter at the end into pascals, and that's one of those conversions. It can just be tricky, particularly, you know, if you're doing it under pressure in an exam or something. So better, I think, to just start in meters, as I've done here. Okay, all we do now is write out the equation that we've seen on the last couple of slides, that stress is force over area, which here now is going to be 500 divided by this 0.01 square meters, and that comes out to be 50,000 newtons per square meter, which is exactly, as Luke said, 50 kilopascals. The kilo here obviously being multiplied by 1,000, just like 50 kilograms is 50,000 grams. So that's the same kind of thing. That's how stress calculations work. It won't get any more complicated than that this year, but what you'll find is you have to remember how to do that in the middle of doing other things. So although it seems fairly straightforward when you calculate the stress on its own, when you've got 3 or 4 calculations and one of them is to calculate the stress, you just need to remember to stick to the program, go with stresses, force over area, and calculate through. I won't get you to go through this example now, but the idea here is to introduce this concept of yield strength, and that means the stress at which something will break, or it'll no longer behave in the same way. But you can kind of think of it as the point at which something's going to break, and that is a material property. So for steel, we can just say the yield strength is 250 megapascals. And what we're really saying there is incredibly versatile. We're saying as long as the stress is less, it's not going to break. And if the stress is higher than this number, it will break. And that's all we need to know. We've already accounted for the force and the dimensions, the scale of the thing. So we'll know whether something's going to break or not. So let me just very quickly work through this problem to show you the kind of thing that I would be doing for it. So we've got, I'll just write down the details. Okay, I'll come back to this paper. I'll call that W, hanging off a circular steel bar, and the steel bar has some kind of diameter D that we don't know yet, and it's holding up 5,000 kilograms, 5 tons, and we know the yield stress. So I guess what we can do first of all is to convert from a mass to a weight. That will be 5,000 kilograms times, I'm just going to use 10 again for gravity, So that's 50,000 newtons. And then I can say, okay, well, stress is force over area. So area is force divided by stress when I rearrange that equation. And then that's going to be, we know the force is 50,000 and the stress we're interested in, well, if we just find the point at which it's just breaking, the stress is 250 megapascals, then we'll know the smallest possible diameter we can get away with. And then we might say, okay, let's double that diameter so that we're not just at the point of breaking. But as long as we know what the limiting diameter is, we can work from there. So I'm going to put down 250 times 10 to the 6 as the stress. And that equals, and again, this is just a calculator job. And as always, I'll keep saying over and over, do make sure you're practicing this calculator work. It's sometimes more complicated than people expect, and it comes with practice. So that's 2 times 10 to the minus 4 square meters is the minimum area which will support that load. Then we need to say, okay, pi r squared, it's a circle, so the area is pi r squared, and that must be what makes up the 2 times 10 to the minus 4 square meters. Again, I'm going to go a bit quick here, but you can practice this rearranging in your own time, that r must be 2 times 10 to the minus 4 divided by pi, all square rooted. And that's something I can put into a calculator. And that comes out to be 7.98 times 10 to the minus 3 meters. And then finally, I have to remember that the question was actually asking for a diameter d, and d is 2 times r. And that comes out to be 16.0 times 10 to the minus 3 meters. And that's 16 millimeters, pretty close. So that's somewhere just smaller than the diameter of that candle that I've been using. I would imagine that's about a 2 centimeter diameter. And this is a 1.6 centimeter diameter in the question, and it's able to hold up 5 tons. So it's kind of a reminder that steel is a very, this is a high yield strength, and steel can support a lot of load, I suppose is what we're really learning. Okay, I'm going to keep going. I'd quite like to finish this lecture by 5. And I think we can do that pretty easily. One thing that we'll come back and think about when we talk about fluid dynamics, we'll look at pressure. And pressure has the same units as stress. It's also a force divided by an area. We tend to use pressure for something that's happening external to an object, and stress describes the internal state. And they're very closely linked. So here's an example. The pressure under an object is the same as the stress at the very bottom of that object. The pressure under your foot is the same as the stress that the sole of your foot is experiencing. So I guess this slide is just a kind of side note. If you're confused by the distinction between stress and pressure, there's very little distinction between the two. Some numbers. The thing that I want you to take away from this slide is that these are large numbers. We said steel breaks at 250 megapascals. So when we're talking about stresses, we're often looking at megapascals or even gigapascals. That's 10 to the 9 pascals, 1,000 million pascals. Carbon nanotubes are extremely strong. So I guess whenever you're working through these calculations, if you get a stress that's comparable to some of these numbers, that's a sign that you're on the right track. If you've got a stress that was like 0.0004 pascals, you might find that that's probably incorrect because it's a very, very small stress, the kind of thing we wouldn't be able to measure. So we've talked about stress. Now I want to talk about strain. When something has a stress, an internal stress, when it has a force applied to it, we've already kind of said it changes length, and strain is a measure of that change in length. And specifically, it's delta x, the change in length, divided by x, the original length. And this is a Greek letter epsilon. I'll put that in the chat as well. And again, that's the lowercase epsilon. So I hope this diagram gives you an understanding of what the numbers we need to calculate strain are and what they mean physically. Obviously, if this was a tensile force, delta x would be an increase in length, and then the calculation would be exactly the same. We said already that stresses are typically very large numbers, strains are typically very small numbers. Things don't change their length very much at all. If I take the candle again and I squash it really quite hard between my hands, it doesn't change length to any extent that we can visualize. So the strain is like 1 part in a million, or even with quite a large force, it would be 1 part in 1,000. And we describe those as being millistrains or microstrains. The other important thing is that strain is a ratio of lengths, and it has no units. So the change in length divided by the length is something in meters divided by something in meters, so it doesn't have any units in the end. And we call that a dimensionless quantity. Just remember that strain is dimensionless. So here is a kind of part-way summary. We've defined stress and we've defined strain. And again, you can do these kinds of questions about metal wires and find how much you expect something to stretch given a certain force, or how much strain there is given a certain amount of stretching. I'll leave that for people to have a go at later, because what I want to look at is this next slide, which is kind of where everything comes together. We already said Hooke's law for springs has a force being related to a change in length. That extends to any material at all, not just springs, using stress and strain as our way of understanding things. So a stress is some constant times a strain. And remember, when you're kind of comparing across these, stress is force over area, so it relates to force, and strain is change in length divided by the original length, so it relates here to this delta x. So there's a similarity between these two equations. The number that relates stress and strain is called Young's modulus, and it's a material property. So steel has a Young's modulus, aluminium has a Young's modulus, different woods have different Young's moduluses, for example. And because stress is measured in pascals, or newtons per square meter, strain has no units, so Young's modulus must also be in pascals, or newtons per square meter. Young's moduli are typically listed in gigapascals, or they're typically very large numbers, as you can see here, and they kind of relate to how hard you know something is. So rubber and spongy materials come out at, say, 0.01 gigapascals. The very hardest materials come out at hundreds or thousands of gigapascals as their Young's modulus. Okay, so one last example in this lecture, and then we've really covered the important information. I'll give everyone 4 minutes to get started on this, and then we'll work our way through it. Okay, I know that's not been very long, but I want to keep on going, so I'm going to bring up the visualizer and just work through some of this. This is me just drawing out the problem. Just remind myself that what's being asked for is the stress and then the extension. One thing, the trickiest thing of all about this question is actually this point here, trying to work out what 5 square millimeters is in terms of square meters. 1 square millimeter is 1 millimeter multiplied by 1 millimeter, and you need to convert both of those millimeters into meters, and so when you multiply it through, you find that a square millimeter is 1 times 10 to the minus 6 square meters. That's something that can easily catch people out. It can easily catch me out So just kind of keep it in the back of your mind for now, I think. Anyway, now what we've got in the problem, we know a force and we know a cross-sectional area. So I think we can calculate a stress in that wire is going to be force over area is 1,000 newtons divided by 5 times 10 to the minus 6 square meters. Which is 200 times 10 to the 6 pascals, 200 megapascals. One of the things I'll just make a quick note of here, you want to get quite good at counting zeros on your calculator or converting things into engineering notation on your calculator. It's easy to misread that kind of number as 20 million or 2 billion, 2 times 10 to the 9. Try not to make those mistakes. So that's the stress. Now what we can do is find a strain, because we know stress is Young's modulus times strain. Therefore, strain is going to be stress divided by Young's modulus if we rearrange the equation. And that's 200 times 10 to the 6 divided by 210 times 10 to the 9. Which comes out as 9.52 times 10 to the minus 4 square, no units. That's a strain, so it's dimensionless. Next up, what we wanted in the end was our change in length. So now we need our other equation, our third equation. Strain is change in length divided by length. And again, we rearrange to get that the change in length is the strain multiplied by the original length. That's 9.52 times 10 to the minus 4 multiplied by 0.75 meters. And that equals 7.14 times 10 to the minus 4 meters. Approximately equal to 0.7 millimeters. So again, you start to see that we're talking about small numbers here. We've got 1,000 newtons, that's like the weight of a person, hanging off this very slender rope with a 5 square millimeter cross-sectional area. And that gives us an extension on nearly a meter's length of less than 1 millimeter. All of these things, these kinds of numbers are going to be important. You can imagine as a designer, you might want to be fitting things together and they'll be under different loads. And if you want them to be really precise fits, you'll need to calculate how much you expect the strain to cause them to expand or contract, and then make sure they fit, even allowing for that expansion or contraction. So, you know, this stuff is central to a lot of design. Okay, there is a summary slide. Obviously, these slides are all on Moodle, so you can, if you're going to remember one set of information from everything we've talked about in the last hour, this is what to remember. Those 4 equations, and that they all link, or the last 3 in particular, the stress equation and the strain equation, can be related together because stress is related to strain. And so often we'll work through problems where we're pulling these things together to find, for example, a change in dimension or whether something's going to break under a given load. This is now the last slide of this lecture. You can now see, I hope, that the kinds of things we've been talking about today would give you some understanding of what's happening in this problem on the bridge. You probably you would have an idea already of what the load on this girder is, and then You would also know its cross-sectional area, and it's been designed therefore to tolerate a certain stress. As it's had this saltwater embrittlement over 50 years, essentially what's happened is that the yield stress has gone down and down and down until the yield stress has fallen below the design stress, and then it broke. So already we're starting to get a good sense of what's going on here, what kind of tools we need to understand the problem. And as we saw right at the start, you've all got the kinds of design ideas, design brains to start putting together solutions as well to that. And then just one more thing is we'll come on and look at finite element analysis, particularly you'll do a whole module around it in second year, and that's where we can use a computer to find stresses in much more complicated geometries. So we're always going to talk about fairly simple geometries like cylinders or square section bars, and there are lots of those things in the world, but there are also some really complicated shapes, and to work out the same kinds of answers for those, we use software analysis that we'll also teach you as part of your degrees. And this image on the right shows where the highest stress would be in a lifting hook, and it's kind of in the crook of the hook, as you might expect. If it's going to break, it's going to break here where the red color bar indicates the highest stresses. Okay, that's nearly completed in an hour. We ended up taking just a bit over an hour. And that is everything that we need to know about stress and strain now. Again, you might just want to look, when you're doing some revision of this topic this week, you might just want to look at some past papers which are linked on the Moodle site, and those will show you the kinds of ways that stress and strain come up in the exam. But it's not particularly more than what we've covered in that lecture and in some of the worked examples from that lecture. Any questions for now? Good question from Luke. When's your first exam? The good news is you've got one exam in this module and it's in May. So what I'm definitely not saying is forget about everything until the night before the exam, but you don't need to be worrying about exams quite yet. I would say take time to get familiar with all the material. We'll cover most of the examinable content in semester one, so you'll then have time to kind of revise it and work with it and really get prepared for the exam. The specific date of the exam will be published, I would think, in around March. We don't do the exam timetables a very long way in advance because it's too subject to change, as this year has proven to all of us. Anything else people want to ask? We'll obviously keep talking about the exam all the way through the module, and just making sure everyone knows exactly what to expect in that. I really don't think exams should come as a surprise at any stage to students. I'm not out to trick you or kind of set you a curveball question. What I want to do is make sure that things like these stress strain analyses, which follow very consistent patterns, always the same kind of analysis, everyone in the class is just really very good at that kind of analysis by the end of the year, and then you'll be asked to do something very similar in the exam, and you just go through it line by line. Generally people do well in the exam because they know exactly what kinds of things are going to be coming up. Okay, let me just switch over my PowerPoint to another one. Okay, this next one's quicker. There's less content. There's only about 10 slides, some of which are just recapping where we've got to. So some of the things that we've done already, in particular, we've talked about notation systems, and we've been using in that first half of the lecture things like I've been talking about megapascals. So we need to know that mega is a prefix, which means multiplied by 1,000,000, multiplied by 10 to the power of 6, and that pascals are an SI derived unit derived from force divided by area, and force in newtons is itself an SI derived unit. So we'll keep talking around things like that, but I hope you're getting a familiarity for some of those units. We've talked about the fact you can add up forces and that you add them up by thinking of them as being vectors, and we'll use that quite consistently. We've talked about the idea that you might, if the force is acting diagonally in your frame of reference, you might want to break it up into horizontal and vertical components, and that can make a lot of calculations much easier. And we've defined what a moment is, and that it's a force multiplied by a distance, and that distance, if you remember from some of the work we did in the last lecture, that distance can somehow be quite tricky to spot. So it's worth doing some practice on moments, and there's tutorials and now tutorial solutions available on Moodle for you there. And then we also talked about Newton's laws. And again, I don't want this to be a module about memorizing things, but it might just be a good idea to try and memorize Newton's laws because they're so fundamental to engineering. If the net force that's acting on something, the resultant force that's acting on something is 0, then there'll be 0 acceleration. We say its velocity will remain constant. Usually, in the context we're dealing with, it will almost certainly mean it's staying still, really. And we can flip that around. If something is staying still, that means the forces acting on it must sum to 0. And Newton's first law here is really what we use throughout this module. Newton's second law we won't use quite so much, but it's still extremely important, and it's kind of the counterpart. If the forces aren't 0 or don't sum to 0, then we'll have acceleration, and that will go be defined by F equals ma. Force is mass times acceleration. And then Newton's third law, for every action there is an equal and opposite reaction. That's actually a more intuitively complicated law, I think, and we don't use it so directly in this module. Okay, here's a question. The speed of light is 3 times 10 to the 8 meters per second. 1 light year is the distance traveled by light in a year. How far is a light nanosecond? Everyone can have a go at this, I think. There's the problem in a different context. So 1 light nanosecond is going to be the distance traveled by light in a nanosecond. Right? If a light year is the distance traveled by light in a year, a light nanosecond, all we changed is the unit of time from a year to a nanosecond, so we can work out that it's the distance traveled by light in a nanosecond. Speed, we know, is measured in meters per second, so that means it's distance divided by time. Just call this speed rather than using letters for it. And so I can say, okay, well, a distance, again, rearranging the equation, is going to be a speed multiplied by a time. And in this case, our speed is 3 times 10 to the 8 meters per second, and our time is 1 nanosecond, and for that we need to remember what a nanosecond is, or what the nano prefix means. That's 1 times 10 to the minus 9 seconds. And when you multiply that through, you'll get that that equals 0.3 meters. So in 1 nanosecond, light travels 0.3 meters. That might seem slightly unconnected to other things that we've been doing. We haven't really been talking about the speed of light or anything like that. But the reason that I want to talk about it is because, first of all, we're looking at units. We said that speed is measured in meters per second, so it must be a distance divided by a time. That's the kind of thing we've been doing a lot of, is thinking of how units can tell us something about equations or vice versa, and that's called dimensional analysis. And then the second thing that we've had to do is to remember what a nanosecond is, and to be able to write down second is 10 to the minus 9 seconds. And also just continually working through, starting with an equation we know or can work out, and rearranging to find something unknown. So all these things that seem unlinked are actually bringing together some similar engineering tools. Okay, let's go back and think about things slightly more related to what we have been talking about. So we're going to want to take these ideas of forces and of stresses and strains and apply them to real things that we might build or make. And I guess one thing that we'll need to know is, how do those forces turn up in the things that we're working with? And the answer is that everything is supported in some way, and forces get transmitted through supports. One thing to have in mind quite a lot here is the work you're doing in fusion as well. I guess at the moment you might still be doing part modeling stuff with Barney, but when you get into putting together joints in fusion, you'll see that you can do things like a revolute joint or a pin joint, or there are about 7 different kinds of joint you can specify, and that relates to some of the stuff that we're talking about here. So do remember that these mathematical ideas also come through in CAD as kind of spatial ideas, and that's linking the physical and the mathematical together. So a simple support is just when one thing rests on another, for example, and that can only give you a force in one direction. So if we draw supports like this, there aren't going to be any sideways forces coming from these supports, only upwards forces. A pin joint is more, has more going on, and pin joints can allow things to rotate, but you wouldn't be able to move this blue bar either sideways on its own or up and down on its own. You can only rotate it. And that means it's kind of pushing back against a sideways force, and it's pushing back against a vertical force. And then a clamped joint where something's completely fixed, you can't move it at all. And so it's pushing back against a horizontal force, pushing back against a vertical force, and it's able to push back if you try and turn it. It can push back against a moment. So these 3 different forces, when we're working, or 3 different supports or joints, when we're working with them, we'll need to mark different forces on our diagrams, depending on what kind of a joint it is. Obviously here I've drawn them all diagrammatically, I've kind of simplified them, but they're everywhere in real life. Again, like I say, all these joints in fusion, which allow you to make actual assemblies that do actual things, relate very cleanly to these kinds of joints here that we're talking about in simple mathematical terms. I think this is important, this last sentence, that one of the skills that you pick up over time, I think, and that to some extent we've been kind of playing with in the quizzes every week, is to try and work out what kinds of motion are going to be possible in a given system or with a given joint. So, you know, there's a small amount of rotation possible here on this bridge support. A bearing like this gives you complete rotation, a 360 degrees rotation, and then this camera can slide and pivot, so it has, again, a different set of possible motions. I guess it can't move in the direction perpendicular to this bar, so there could be a force that pushes back against anything in that direction. So this is kind of what we've been saying. If a support prevents you moving in a certain direction, that's another way of saying it can provide a force in that direction. So these simple supports here prevent the red bar from moving downwards. That's the same as saying they push upwards. This pin support prevents the blue bar from moving its origin point to the left or down. That's the same as saying there's a horizontal force and a vertical force available there. And similarly, we've already said this clamped joint stops three kinds of motion, and so it provides three kinds of force. And then that's all useful because we know this principle of equilibrium that we've talked about already, that the forces acting on something, if it's staying still, have to add up to zero. Well, that's good because we can write down some forces acting on things now and use that to add up to zero. Similarly, the moments acting on something have to add to zero if it's staying still. And again, we can use that to write down an equation and we can start to find some unknowns. I just want to bring up one more thing now about weight. We've already used weight is mass times gravity a few times. I hope people have started to get a good feel for that. We'll use it a lot more, so you'll get used to it in the end. But this is kind of an important point, that weight acts through the center of gravity of an object. And we can calculate that center of gravity, but usually it's kind of obvious it's in the middle of the object, certainly for simple shapes. And so, for example, if I just stop sharing for a second, again, if I look at the candle, the center of gravity should be about the point at which it balances. It's in the middle of the candle. And, you know, again, that's something that intuitively people just know. But it means that we can mark an arrow for the weight wherever we think that center is. And that'll help us to start marking up our diagrams even more. So here is an example that I want people to have a go at. And we'll leave 7 minutes for this. It's 23 minutes past on my clock at the moment, so we'll come back and look at it at past. And at that stage, we'll be nearly done. I'd like everyone to start by drawing a diagram, marking on as many forces as they can based on some of the things we've just been talking about, and then seeing if you can write down equations which would help us to work out some of the forces we don't know. So I've just put that system as a list of steps in the chat window. So those are the steps that I want people to be working through just now. Okay, that's past. Did anyone get to any answers for these forces that must be at A and B? Let's take a look then and kind of work through it from the start. So here's my diagram. I've tried to mark on lengths where I can. The weight of the beam itself is 15 kilograms, which I've converted up here as 150 newtons, and that is acting in the middle of the beam. That's what we talked about that idea of a center of mass. So the center of mass is in the center of the beam. The beam is 6 meters long, so that's 3 meters from either end. There's also this other load, which is kind of like something resting on the beam, and that's 5 meters from one end, 1 meter from the other. And these are the two unknown forces that the supports, we said, can push upwards, and so we'll mark on forces acting upwards there and there. Okay, if we now start to think about equilibrium, one of the things that we're going to do a lot is to say the forces acting upwards must equal the forces acting downwards. And I'll use this kind of a double-headed arrow up and down to indicate that that's what I'm doing. So the forces acting upwards, that's RA and RB on my diagram, which I guess is a free body diagram of the kind that we talked about last time. And the forces acting downwards are 150 plus 270. This force and this force, the two weights that are marked on the diagram. So that comes to 420 newtons. We've got two unknowns here and only one equation. So we need another equation. We might think about the forces acting sideways, but there are no forces acting sideways. So I can mark that on as well. This is horizontal equilibrium, no forces. I just put it in brackets to indicate we're not really using that, but we thought about it as a possibility. So the third thing that we're going to be able to use at each stage is moments. And I'm going to take moments about the point A and say the whole thing isn't rotating about A, and therefore there has to be moment equilibrium about that point. And what I'll do is go along the beam from A, accounting for every force and the distance from A that force acts. And so I'll get 150 times 3 meters plus 270 times 5 meters minus RB times 6 meters equals 0. There are 4 forces here. This force, the reaction at A, goes straight through A, and so it doesn't turn up when I'm looking at the moment calculation about A. That's a force that goes through the pivot, so it doesn't contribute to the moment. We touched on some of that when we were talking about moments last time, but that's something that takes a bit of thought and practice of examples like this to really just get comfortable with. This force here is 150 newtons. It's 3 meters away from the pivot, and that's accounted for there. 27 kilograms is 270 newtons, 5 meters away from the pivot, accounted for there. And those are both acting clockwise. They tend to want to turn the beam this way around A, but then the reaction force here is kind of pushing upwards, so it's turning the beam anti-clockwise. And so I've given it a negative sign here. All of those moments, that's all the moments that are acting, and they must therefore sum to 0 because the whole beam isn't rotating. So we can rearrange this to say 6 times RB is 450 plus 5 times 270 is 1,350, which equals 1,800 Newton meters, and therefore RB is 1,800 divided by 6 is going to be 300 newtons. If we just now make a note from here and jump down, we know that RA plus RB equals 420 newtons and RB equals 300 newtons. So RA plus 300 equals 420, and therefore RA equals 120 newtons. And those are our two answers. Luke, is that what you got? I'm not seeing an answer in the chat, so I'm gonna cool. So that is exactly right. Fine to leave it in terms of G, and then you would get, I guess, 30 times G and 12 times G, 30 kilograms equivalent and 12 kilograms equivalent. Those kinds of questions turn up a lot. And it's always the same steps, the ones I put in the chat. Draw the diagram, mark everything up as well as you can, make a note of what your unknown forces are, use vertical equilibrium, use horizontal equilibrium, and use moment equilibrium to write down as many equations as you need, and then solve those equations to find your unknowns, which in this case were the two reaction forces, RB and RA. Okay, we're nearly done with new content for today. There's another example here. I'm going to go through. Again, it's all on Moodle. You can see my work solutions already on Moodle. But I do just want to bring up, I'm just drawing out my diagram here. And I'll reload up the visualizer. This is one of those ones where it's a clamped joint at the wall. The beam is fixed over here, and that means there can be a vertical unknown force here, a horizontal unknown force here, and also an unknown moment here. And so this is now the diagram that you have to start with and then work out what all three of those unknowns are to solve that particular problem. Just a couple of other things to think about. If there are only two forces acting and an object is in equilibrium, then those two forces must be equal and opposite and in the same direction, along the same line. And that can sometimes be a useful thing to remember. This one here is a bit more complicated, to do with if there are three forces acting on an object. We won't use that directly, but again, it's just a way of remembering that all of this is linked to the maths of geometry, I suppose. And then there's another question there. My sense is we've probably done enough worked examples now that people are starting to feel it. So I won't go through this, but I'm happy to go through that to start next week if people want to flag that up. Finally, you may occasionally see problems that don't fit into this way of understanding things. Sometimes you've got too many unknowns and not enough equations. In this picture here, we don't know how much of the force, the reaction, is split between each of the four supports because we just don't have enough equations to work it out. And in this one here, there's a sideways force from the applied force, but we don't have anything to balance that sideways force, so the whole thing would accelerate. So although mostly when we work through problems, we'll be working with problems that fit the models we're looking at quite well, it's worth remembering that not everything will fit into the current way of understanding things. And that's why over 3 years, we'll have to keep on trying to build up more and more engineering to see, for example, what happens in a situation like this one. Okay, that is everything from that bit of the class. Any questions from people that you want to raise now? Good. In that case, there's just one last thing for this week. There is on the Moodle site in Equilibrium and Simple Structures this week's quiz, and it's available now, I hope. And if everyone can have a go at that quiz, then that would be great. And again, do have a think about how some of these things in the quiz will relate to what we've been doing in class this week. I put the link in the chat just in case anyone can't find it.
Question 5 is worded. Is it like which weight would pull the other one up, or which weight will go down?
I suppose you're right. I suppose it could be better worded as which weight will pull the other one up. Good point. Okay, that is 7 minutes. Let's take a look. If everyone can submit, we'll finish up just by talking about some of the answers. Okay. I hope that the written explanations that you'll see when you submit help you anyway to understand what's going on. I just wanted to flag with this example what we're looking at here. You can't quite read it in this box unless you know what it says, but this box says stress and this box here says megapascals. The color bar on this particular plot is actually showing us the stress in this system. And so the kinds of things we've talked about in the lecture today feed through into fairly realistic problems like this, where we're looking at which of these things is going to break first. And it's by understanding stress and strain that we can understand those problems. Pendulum problems are the kind of thing, again, that can be intuitive, but can also be kind of tricky. Usually the way to think about it is the longer the pendulum, the smaller the losses in comparison to the energy that's in the system. But that's something that takes some time to convince yourself of. One way to get more of a feel for this is to imagine a really, really long pendulum and a really, really short pendulum. So exaggerate the differences and see if you can convince yourself that the short one will actually stop quite quickly because the losses are quite high compared to what's in the system, and the long pendulum will swing and swing and swing for days. These kinds of CAM problems are, again, a thing that comes up a lot in engineering, where if you have something rotating off its axis, so this second disk, the red disk in particular, is clearly rotating on a non-central axis, then that means that the blue slider is going to go up and down because it rests on top of the red disk. I guess that might be visible in this animation, which again is a bit jerky, but you can see some parts of what's going on from the animation now. And so the second system, because the disk is rotating about a point further from its center, it moves away from its original position further, and that means the rod moves further. Question 4 is the kind of thing that I hope people can sort of see already, because it involves picturing different triangles, and that's something that I think is coming up in maths around about now. But the wedge is 1 millimeter in the direction directly across its length, and if you draw directly across its height, sorry, and if you draw the correct triangle, you'll see that that means it's more than 1 millimeter vertically that it's holding up the green tube. And again, exaggerating in your mind the scale of things will help you to picture some of that. And question 5, as Philippa said, it would be that one weight will pull the other one up, really. Is probably a better way of thinking about it. But actually, in this context, neither weight will move either. The weights won't move because they're the same. If you imagine cutting a slice in this rope here, and then thinking about how much force you need to hold everything still, that force is W in both cases, and that is the force, the tension in the rope. As always, those are kinds of like brain teasers to try and get people to think of lots of different ways of using fusion and lots of different ways of using engineering. And I hope they'll keep on linking back to some of the things that we're talking about in this class. But really the important thing is just that you see that engineering involves visualizing physical systems in some way. Any questions before we leave it?
No, I think it's all good.
Cool. Thank you all then. That's been a good session. As the semester goes on, you'll probably find more and more things that aren't making sense, or that it's more and more annoying when I'm talking about something that you can't see because it's my hand's in the way or something. So do get happy to shout things out during these lectures, and I'll be very happy to hear all feedback at all times. I think we're back next week, aren't we? We've got another session next week before we have any breaks. So I'll see you then, and we'll be talking about how to build up some of these ideas into structures. So rather than looking at one object, we'll look at interconnected objects and how they work. And other than that, have a lovely week, and I will see you all soon, I hope. And bye.
Bye. See you later.
Bye. Thanks.
Thank you. Bye.